Okay, let's have a look at the tensile testing of different materials. Now, why we need to do the tensile testing? Why we need to find the properties of the material to make sure we know the failure point, we know the failure stress, we know the yield stress, we know the yield point. So we can work within the factor of safety. We can also find out the elastic energy and the plastic energy absorbed by the materials. Now, if you want to test a material, either we can do compression or tension. Now, or we can do bend test. Depending on the material properties, the material can be either strong or weak. If the same material has higher like a different tensile strength, it doesn't mean that it has exactly same compressive strength. The material, they act stronger in compression as compared to in tension. In bending, obviously how much force you have applied to bend the material. Then there is another thing which is called the toughness of the material, energy absorbed by the material until it fails. We'll talk about that one. Now, when we do the tensile testing, we need two things. We need the length of the specimen and we need the area of the specimen. The length and area. Length will give us how much the material is elongated. Area will give us how much the material has reduced in the cross-sectional. Now, known as necking. Now, if I want to find out the original area, I can do original area is pi r square or pi d square over 4. Final area, when we measure the final area, we measure it very close to the failure point, and we call it pi d square over 4, where df is the final diameter, d naught is the initial diameter. Now, on the graph, there are certain points that are very important. You see, this point over here is known as the yield stress or yield point. The stress at yield point is called the yield stress, and the strain at that point is known as yield strain. If you remove the load, the material will come back to its original position. Hence, this is the reason we find the elastic modulus. Now, the final strain is known as that one, strain final. This symbol is known as epsilon. If we want to find the ductility is given by this formula, the final strain multiplied by 100%. Whatever the value of the final strain is, if it's, let's say, 0.07, you multiply that by 100, so you will have an answer of let's say 7% ductility. The more the material stretch, the more the ductile the material are. The ductility can also be calculated by the change in the cross-sectional area as well, but you will have different values. If one is saying the value is, let's say, 7% ductile, cross-sectional area might say 6 or maybe 7 or maybe 8, it will be different. It might be same, but it will be different. The reason is because it's very difficult to measure the cross-sectional area straight away, as you have done this morning. If the material is very brittle, that's the type of the failure you will see. If the material is ductile, that's a type of the failure known as cup and cone failure. Now, the higher the ductility, the more safe the materials are. They give you a factor of safety. They give you a warning before they actually fail. The deformation is seen as a form of the warning because it absorbs the energy, it deforms, and you know like something is going to fail, so there is a little bit warning. In a brittle, you will not see any warning. Okay. Brittle material, they have a ductility less than 5%. Ductile, they have ductility more than 5% as a rule of thumb. Now then we got the resilience. When we apply the force, the material will stretch. When you remove the force, they will come back. Now you are doing the work done. Work done is force applied over a distance. Force applied and you move the distance. So this one I applied the force and this was here. It's actually moved back. So the distance move is that one and how much force I've applied. If the material is resilient, it can absorb a lot of force and it won't fail. Now when we have a look at the modulus of elasticity has this formula. Sometimes this formula is written as elastic modulus is stress over the strain, where stress has a unit in megapascal, strain has no units. So the unit for the elastic modulus is going to be same as stress, megapascal, sometimes gigapascal, but mostly mega gigapascal. So we got that value. Now I will come back to this one in a minute. Now when we look at the upper limit on the stress, which is known as, let me just clear that screen. Elastic modulus, we measure the elastic modulus in this region. That is a region where we measure the elastic modulus. Now, whenever we measure a stress, whenever we measure the stress in the material, there are two different types of stress strain graphs. This graph here is known as engineering stress strain graph for a ductile material. The true stress strain graph something look like that. That is the true stress strain graph. So after this point, it should go up, but it's coming down, and there is a reason for that one. If there is a graph where you see, oops, sorry, doesn't work that one. If we have a material that is a very ductile and it's a polymer, the graph will something looks like that, because there will be massive strain, and then material will fail. But this is not going to be as tough as compared to the steel or the other material. Now, if I want to find the resilience, this is the equation for the resilience. Half sigma y square over E, where sigma y is the yield stress. Where we find the yield stress? The yield stress is that point, this point here, and you just find the corresponding yield, and that will be the yield stress, where E is the modulus of the material. I will show you how to find the modulus and how to look at the yield stress of the material. But this formula will give you the resilience of the material. If there is high resilience, the material can absorb more stress without yielding. It's not going to yield. If the material has high modulus, very high value of modulus, then the yielding, the resilience will become less, because now you're dividing with something a high value, so the resilience will reduce. Just to give you some resilience value, the rubbers has a resilience values of 2.5. The reason is because rubber has very low value for the elastic modulus. Ceramic has a very high elastic modulus value, hence its resilience values is very low. Okay, so this is from MSc, Material Selection Charts. It's all available online. You have used that in your first assignment, so you can use that one if you like to, but make sure you reference that one. Now, toughness is not the strength. Toughness is how much beating the material can take before it starts to yield. Now the example I give is, if there is a boxer, one boxer is getting a lot of beating without just saying I give up, that he's a tough guy, because he's getting all the beating but still not yielding. He's not saying like that's it. That is the toughness. Toughness is where the material absorb the energy without being yielding. So there is no yield strength is quite high. Now then there is another very important formula, which is here. Now this value here is known as yield strength. This value is known as tensile strength, and this is the strain at failure. So this value comes from here. This value comes from the top point of the graph, and this value comes from here. Okay, now what is this? Let me just explain in a minute. Okay, now these are toughness tests. Toughness test, we use that one to test, which is called impact testing. These are ISOD and a Charpy, two impact testing. Impact testing, we have a hammer, we release the hammer goes, hits that sample, and then the sample breaks, but the hammer rise on the other end. It loses some of the energy, and this energy is absorbed by this material. Hence, we can say the material is tough or not. If that was a pencil wood, the hammer is going to go maybe all the way up till here. The change in height is not too much. But if that's like a titanium, very hard material, tough material, the change in height will be a lot more. Okay, now this one. If I want to find out, this is the zoom. This is from the test, today tests. So I've just plotted the graph. Now here, this is a normal version, and that's the zoomed out version of that one. If I want to find out the value for the Young's modulus or elastic modulus, I zoom this graph out, and that's what I got. I need to find out that value, and I need to find out that value. So here I got the value, let's say, is 27 megapascal. Yeah, because the equation is the stress value I got from here, 27 megapascal, and the strain value which I look here is 0.0005. So let's say 0.0005. Yeah, you all will get a different value based on how you read the graph, and that will give me the elastic modulus, and I can press an ENG and it can give me in gigapascal, and I can convert mega into giga. That's that one. That's how we find the E. Now if I want to find out the sigma tensile strength, it's the highest value on the graph, which is here, which is 70 megapascal. If I want to find out its failure point, failure stress, is that value. The stress at failure is going to be 60 megapascal. This is the point where necking start to happen, this value. If I want to find out the total ductility of that one, let's say whatever value I got, let's go with 0.12, 0.13, let's say 0.13. I need to multiply that by 100 and 13%. So material is 13% ductile. Yeah, okay. Now here there are some equations you can actually use to find different values from this graph. So Young's modulus, you can calculate the Young's modulus, which I did. Yield strength, which is the strength here, 27 megapascal. I got that one from here. Tensile strength is that value, 70 megapascal from the graph. Modulus of resilience, this is the value, this is the equation for modulus of resilience. Sigma y, what's the sigma y? It's that value. Yeah, sigma y square over 2e. Where is the e? You calculate the e in this part. Then ductility is simple and easy. Then toughness, this is the formula for the toughness. Toughness is sigma y plus sigma ts divided by 2 multiplied by the strain. Yeah, multiply by the strain. Strain value is here, 0.12. And that's it. Okay.